The project we have undertaken is to design a protective berm and actuation pond around Thomond. The location of this protective berm and actuation pond is shown by the following red line. We can see here a close-up of the site for the actuation pond. A trial pit was dug in the location shown. From this trial hole we could see that there were 4 distinct strata. The first layer was topsoil fill, which extended to a depth of 550 mm. The second strata was the original topsoil, which extended from 550 mm to 1100 mm. The third layer was a 100 mm layer of peat. The fourth layer was a layer of grey silt extending from 1200 mm to the bottom of the trial pit, which was 2000 mm. At 1300 mm we encountered perched water. On intact samples, an in situ shear vein test was carried out. From the excavation we took samples of each strata for analysis. Collaboration between groups led us to obtain further soil samples, of which were below the depth of our trial pit. These samples were oven dried for a week between laboratory sessions. They were then broken down into their individual particles as shown here. It was necessary to riffle certain samples to accurately obtain a more manageable sample. A sieve analysis test was undertaken on each of these samples. The results were tabulated and graphed to give us a grading curve for each sample. Due to there being granules of soils apart from individual particles, inaccuracies were encountered. A proctor test was undertaken to obtain optimum moisture content values and relative compaction. This was done by filling the mould in 3 equal layers and compacting each layer 27 times with a 2.5 kg hammer. The collar was removed and the sample and mould masses were found. Samples of each mould were taken to obtain the moisture content at that compaction. The results were graphed to obtain the proctor curve for that soil sample. Possibly more tests at varying moisture contents should have been carried out to obtain a more accurate result. A CBR test was carried out on the pink clay to obtain its bearing capacity, as this soil could potentially be used as a foundation for the berm and actuation pond. An initial process similar to that of the proctor test was carried out, except a 5 kg hammer was used and the number of blows per layer was 67. It was then put into the CBR testing machine, which resulted in an indentation as shown. We measured the penetration of this indentation in proportion to the force causing this penetration and graphed our results. We then proceeded to the Atterberg limit tests, consisting of the plastic and liquid limit tests. The plastic limit test consisted of rolling a sample of soil to a 3 mm diameter. If it crumbled before it got to this diameter, it was too dry. If it didn't crumble when it got to this diameter, it was too wet. When it crumbled just at a 3 mm diameter, this is your plastic limit, and the water content of this sample was obtained. However, this is an empirical test, which can often lead to inaccuracies in results. The liquid limit was found using the cone pentrometer method. This consisted of allowing a metal cone penetrate under its own self-weight into a homogeneous sample of soil and the penetration measured. The moisture content of this sample was found and repeated for varying moisture contents. The liquid limit was determined from a graph of penetration versus moisture content, where a value for moisture content corresponds to a penetration of 20 mm. We developed a schematic design showing the cross-section through the beam. We then calculated seepage rates through the dam with a factor of safety of 2 in mind. However, we did not require to calculate the seepage under the berm, as we will be placing an impermeable layer underneath the berm. The seepage slope is 30 degrees, however, we changed this to 26.56 degrees to allow for slope stability, as the standard berm slope is 2:1, giving us an angle of 26.56 degrees. This is a standard flow net diagram for a berm. We calculated using Casagrande's method the location of the phreatic surface for our model. This also aided us in obtaining a preliminary size for a drain which will be required to control the seepage flow to prevent erosion and piping. We analysed the hydrostatic pressure on the sides of the berm caused by the water and compared this to the frictional resistance of the berm to prevent sliding of the berm. The design of the foundation for the berm required further analysis to determine whether or not base heave would be an issue. The issue of swelling soils was looked into and how the integrity of the berm could be compromised due to this phenomenon. Upon extensive analysis of the flow net, if it turned out that there was an excessive amount of seepage through the berm from using on-site soils, an option could be to line the base of the pond and the inside side of the berm with impermeable membrane, hence preventing any unwanted seepage.